Now let's take a look at using the Gauss-Seidel method to approximate a solution to a system of equations. The Gauss-Seidel method is quite similar to the the Jacobi method that we looked at earlier, with one difference that you'll see as we proceed. So the first thing we need to do is solve each of these equations, solve the first equation for x1, second one for x2, and the third one for x3. So let me go ahead and do that. So there are the three equations solved for x1, x2, and x3. The next thing I'll do is make a table that we'll use to keep track of our values. So you can see, like last time, I'm starting with initial values of 0 for each of x1, x2, and x3. The choice of 0 is arbitrary. We could choose all three of them to be 1 if we wanted, whatever we'd like. So now let's go ahead and compute the second values of each one. So when I'm computing the second value of x1, I use the most recent values of x2 and x3, which are both 0. So in that case, then, x1 just gives us 12 over 5, which is 2.4. But now when we go on to compute x2, we use the green formula up above and to the right. But we now have a new value of x1 rather than 0. So let's use that new value. So we have negative 25 minus 3 times 2.4, which is the most recent value of x1. The most recent value of x3 is 0. So we have 2 times 0 there in that spot. Okay, and we're dividing by 8. And when we do that, the value we get is negative 4.025. Okay, so that's our second x2. And now for our second x3, we again use our equation above and to the right, but we use the most recent values we have for x1 and x2. So we have 6 minus 2.4 minus negative 4.025. And that's all divided by 4. And that comes out to be 1.90625. So those are our second values. Remembering that the actual values of these things are 1, negative 3, and 2, we can see that the x3 is pretty close right now. And of course, that would make sense because it had the advantage over the other two of using the updated values of x1 and x2. When we go on to our third iteration, all right, I'm not going to have room to squeeze everything in here, but let me see what I can fit. So the x1 is going to be 12 plus the most recent x2. So that's from our previous steps, that's negative 4.025. And then minus 2 times our most recent x3, which is the 1.9 da da da. And it's all divided by 5. And that comes out to be 0.8325. Now, when we go on to find our third x2, we'll go ahead and use that 0.8325 value that we just obtained. So we'll have negative 25 minus 3 times 8, or 0.8325, and then plus 2 times that value we had of x3, which was 1.9, etc. And that's all divided by 8. And the result of that is negative 2.960625. And in the interest of room here, let me just tell you what we get for x3 this time around. We get 2.03, 203, 125. So again, remembering that the actual value of x1, the exact value, is 1, we're off by a ways there, but x2, the actual value is -3, and you can see we're pretty close, and the x3, the actual value is 2, and so we're quite close there. If we were to go on one more iteration, so when we go to the fourth iteration, the value we obtained for x1 that time comes out to be 0.9950625. So you can see then we're very, very close to the actual value of 1, and you would imagine that our x2 and x3 will be even closer to their exact values as well. So that's how the Gauss-Seidel works. Again, it's quite similar to the Jacobi method, except we constantly update all the values, and for each computation we use the most recent values obtained for the other unknowns.